So before we start, is there any questions so far?
Yes, I have a question.
Yes.
You talk about scattering make resistivity proportional to the T power 2, right?
Yes.
But in this derivation, there is no mechanism. So we don't know that it's electron-electron scattering or electron-photon scattering, right?
Of course, the mechanism is sort of implied here because we are talking about electron-electron scattering. It cannot be phonon. Okay. So there are almost free electrons, almost near, the edge of the Fermi surface. So there are free electron scatterings. That's the first order approximation. So if this is not Coulomb, then what else?
When we learn the scattering theory, I think there's an interaction Hamiltonian, right?
Of course, there's a, but here we sort of make very crude approximation, right? So we consider this kind of interaction strength to be like constant in K space. Okay, so that is a reasonable assumption for almost free electron. Yes. Okay, of course they interact, in real space like 1 over r squared, right? But in K space, it is almost a constant.
Can I say, if we apply this theory in the metal, I think potential is a constant, right?
Right. So if you like to be more precise, then this, potential in K space is something like, screening potential. So KTF refers to Thomas Fermi momentum, if you remember correctly. And this is a Fourier transform of the Coulomb potential in momentum space. But remember, all the electrons are very close to the Fermi surface. So then what is the value of K? Simply is KF. And so in that limit, this is almost a constant. So then this something in between in K space is certainly just a constant scattering potential. Is this what you're concerned? Okay, so I'm telling you that you don't have to worry about this because near the Fermi surface, this potential reaches almost a constant. It doesn't matter that tiny difference different from the constant. So to the leading order, so we can simply just approximate this as a constant scattering potential. Okay, so but this is a good question. So we need to understand this microscopic mechanism, right? Okay, so now we understand this, then we know why this resistivity goes like t squared. Good. So any other questions? So if not, so let's just start the second quantization discussion. And as I promised that we will learn how to count this particle number, but we need to first start from this Schrödinger picture, which is the first quantization of a quantum particle. And so let me just start from the beginning. So this is a second quantization. But we need to start from single particle quantum mechanics and imagine that we have a single electron living inside a box satisfying this Schrödinger equation or eigenvalue equation. So we have done that already, and this potential is kind of a rigid wall of the box shape, so that inside the box the electron is free. So the eigenvalue or eigenstates is labeled by this U of R with the subscript alpha, and alpha runs from 1 to 3 to n. So in other words, you get some sort of many energy levels of a single electron. So there's just a single electron here. But we could solve for this Schrödinger equation for a single electron and its eigenstates. And the eigenstates are very simple because this is simply just, this plane wave like nk alpha. So you got a bunch of plane wave as your solution, so that's easy. But let's just start from the easiest part, and I will start to add some complications. And we have an orthogonal and normalization condition, orthonormal, for these eigenstates, because from this quantum mechanics, you know that. For different eigenstates labeled by different alphas, alpha and alpha prime, or different eigenstates, and the product is u star alpha and u alpha integrated over the entire space is actually normalized to delta r alpha prime, right? So this is 1 if alpha is the same as alpha prime, and 0 if not the same. So this is single particle quantum mechanics. So now we try to do some tricks, and we play some tricks. Okay, so the tricks involve the Dirac notation. So remember your quantum mechanics. So that's why you need to take quantum mechanics at least 1 or 2 before taking this course, because you should be familiar with the Dirac notation. For example, this Bragg state and Cat state, right? So you should know what they mean, right? So this is a matrix, the column row matrix representation of a quantum states. So the Bragg state is this, and the Cat state is the right notation. And the Bragg state represents a quantum states in real space, but in a discretized version, so that the wave function takes this kind of discretized values. So remember in quantum mechanics, you have some distribution of wave functions in space, and it represents the probability distribution of finding such a quantum particle in real space. But in Dirac notation, we could discretize this kind of wave function in such a way that it consists only, some kind of discrete points. Imagine that there's no curve. And I simply just remove the curve and only consider discrete points. Imagine that there is only many points in the real space, and the simple cross here represents the probability amplitude of finding such a particle in real space. And suppose we don't know the shape of that data point, so they're just data points. And we could equally well to represent such a Schrödinger wave function in terms of a discretized, matrix form. And that is the essence of a Dirac notation, that we use the column or row matrix to represent the quantum states in, both X and K space. And here, suppose that this is in real space, and all these, values as a matrix element of this row matrix is nothing but the values in the y-axis here. Okay, you simply just collect all the discrete points and the values of these wave functions at that particular points, and then you call this Dirac, say, Bragg states. And likewise, if you use this column matrix, and this is a Dirac Cat state, and Bragg and Cat states are complex conjugate to each other, right? Because the Hermitian conjugate of this say I should use this star, is that the row matrix becomes a column matrix, and you take the complex conjugate of the matrix elements, and so they are Hermitian conjugate. Okay, so we take advantage of the Dirac notation, and we could rewrite this orthonormal condition for a single electron living in a box, and this is given by, suppose I have this, real space, and I could simply just, divide this real space into different small volumes or small unit cells, and I could call this delta omega as size or the volume of this small unit cell. And so each point or each unit cell represents, in real space, each point here, xi. Okay, so this is xi. So the xi occupies a small volume in real space. And I can discretize this real space in terms of many small volumes, and this integral over the real space variables could be re-expressed in terms of a discrete summation. Okay, so the continuous integration now becomes the discrete summation, and inside the summation we have this matrix product between this row matrix and the column matrix. Okay, so if I use this Dirac notation, this is nothing but U start alpha R1 U star N and U alpha R1 U alpha Rn. Okay, so I did nothing. I only rewrite this integral in terms of a discrete summation. So that's all. Okay, nothing has changed. It's identical, right? Okay. Everyone clear? Good. So, but now the magic starts. So now I could simply just use this basis, the orthogonal and normalization condition. Now takes slightly different form. And I call this state, this row matrix, a Dirac broad state, and the column matrix as a Dirac cat state. Right? So this is prime, prime, prime. Yeah. Okay. So the complicated summation of this matrix product becomes very, very simple, just one line and a couple of letters in terms of a simplified orthonormal condition that the product between the Dirac broad state and the cat state is normalized. Okay, so I rewrite this integral in terms of this matrix form. So the tricks start to set in because I could simply just repeatedly use this Dirac notation to rewrite this kind of a scattering potential. Okay, it's a two-particle scattering or a single particle potential in terms of creating a particle or destroying a particle. Okay, so everything starts from the Dirac notation. So that's really a useful convention. Good. So now I have another very useful identity, which is the completeness of eigenstates. That if I take the product between two matrices, one is Dirac cast state, another is Dirac broad state, and I get a unit matrix, which is n by n. And that is also identity in quantum mechanics, which shows that the eigenstates are complete. Because and by the matrix product, remember that if this is the column matrix, this is n by 1 matrix, right? And if this is a row matrix, this is a 1 by n matrix. So you multiply n by 1 matrix by a 1 by n matrix, and you end up having an n by n matrix, right? So this is very different from this normalization condition where you actually make a product between a row matrix on the left and a column matrix to the right. And when you do so, this is n, 1 by n times n by 1. And at the end of the day, this is just a 1 by 1 matrix, which is a number. Okay? And this is another powerful notation that Dirac invented, because you can simply just, by looking at this notation, whether this cast and the broad state and their orientation of these two symbols, you would immediately know that whether this is just a orthonormal condition or it's a completeness. Okay? So when you do this completeness proof, remember this kind of angle is actually along the opposite side, but this kind of notation, if you put it on the two sides, and this is kind of a inner product. Okay? So again, by using this Fourier theorem, but we could rewrite this any quantum state in terms of a Dirac broad state or cast state, and we know that any arbitrary wave functions in single particle quantum mechanics could be expanded in terms of, suppose this is a cast state, linear combinations of those eigenstates. This is a single particle eigenbasis. Okay, so this is a Fourier decomposition theorem, which says that any arbitrary quantum states is a linear combination of eigenstates with a proper coefficient in front, and you sum over all possible eigenstates. Right? Okay. And that's the great simplification of the single particle quantum mechanics, because this is what we need in order to construct the second quantization operator. So there is no official name for the second quantization because there's no such a thing as a second quantization. Everything is the Schrödinger equation plus Dirac notation. So that's all. Quantum mechanics is what we only need. We don't need something else for this second quantization. So there's no such a procedure as a second quantization. Okay. So the only thing that we call the second quantization, only reason is because it looks like a completely new concept in quantum mechanics, that we could use the operator to actually increase the particle number or decrease particle number by 1. But apart from that, everything comes from your quantum mechanics. Okay, so it's all about quantum mechanics, nothing else. Okay, so let's take a short break. When we come back, we will, play more tricks by using the Dirac notations and construct the single particle scattering potential. Okay, so if you're not familiar with these tricks, please review your quantum mechanics 1 or 2. Right, so you should know that even undergraduate quantum mechanics, we will introduce the Dirac notation. So let's start to play more tricks. Suppose that we want to, evaluate some kind of single particle potential. So V refers to the you could consider this as just a potential well, potential step, potential barrier, whatever you like to imagine in the single particle quantum mechanics. So V represents the potential which acts on only a single quantum particle. And suppose in quantum mechanics we like to evaluate this excitation value of such a single particle potential, what we do is just by following the Schrödinger equation, right? Schrödinger picture, that we simply just perform such a integral, right? Okay? But now we should rewrite this type of a expression value in Schrödinger picture in terms of the Dirac notation. So that's all the magic comes about, because we could use the Dirac notation to represent this V wearing a hat. So in terms of this kind of a single particle potential, so we could have such a kind of integral in our earlier notation, right? Remember that. Okay, so this U alpha represents the eigenstates of a single electron in the box. Suppose we simply just use this eigenstates to evaluate this potential, expression value of the potential for the single particle scattering. So then we could take advantage of this Dirac Broglie cascade. So suppose I have an incoming, say, electron carrying this quantum number alpha living inside of a single box, a single electron, and then there's some kind of a potential. Presence inside the box, and because of this potential, this incoming electron state is changed to the state alpha prime as another eigenstate, because electron can only occupy in their eigenstates, and they have different eigenstates. I can label them with different labels. Suppose that incoming electrons is at alpha states, and outgoing is actually alpha prime. And the reason why electrons change their eigenstates because of the potential. Okay, this is a single particle potential. Suppose we have that. And in terms of Dirac notation, this is nothing but the matrix element, because this tells us that you can consider this potential operator in such a single electron living in a box as a matrix form. Okay, so the matrix element of this V operator just tells you the amplitude of each individual scattering processes, right? Okay, so for example, if I have an incoming electrons and hit this potential, and then it gets scattered, and the initial state is actually alpha, and the final state is alpha prime, and the amplitude associated with such a scattering process is called V alpha alpha prime. And there are infinite number of such possibilities. So you can imagine as alpha runs from 1 to infinity, and alpha prime also runs from 1 to infinity. So I have all kinds of possible initial state and final states for the single scattering events, so that each event may have different amplitudes, right? So this is a number. So this V alpha alpha prime is a number. But I got infinite number of numbers like this. Okay, so this is V11, V12, V1n, V21, V2n, Vnn. Right? Okay, so imagine that I have infinite number of possible initial and final states associated with that single particle potential. and I can use a matrix to represent such a potential scattering. So now I could simply just, again, use the Dirac notation to rewrite this V in terms of that matrix. So what is this matrix? Well, let's play the magic. Okay? So by using the Dirac notation, we could simply use this, completeness theorem. Okay, and as I mentioned already, in the completeness theorem in quantum mechanics, I could use the direct product between this Dirac cascade and Brat state to represent the unit matrix 1, because this is simply just a completeness theorem in quantum mechanics. And I can insert this 1 everywhere I want, whatever, whenever I would like to. If I would like to insert, many unit matrix, and so be it. Okay, I can put it here. I can also put it here. Yes, but of course, when there are two identity matrices, so I use different labeling to label this eigenstates. So the second unit matrix, is in terms of this different eigenstate. Labeling alpha double prime. All right? Okay. Nothing is mysterious. It's just quantum mechanics, Dirac notation, nothing more. But you'll see the magic in just the following lines. As I mentioned, this this V alpha prime represents the matrix element of this complicated Dirac matrix form. I can just encircle this, head-to-head, this Dirac notation in a completeness theorem, like this or like that. But I can also do it in a different way, right? So if I do it this way, then, and that would be a new way to understand this identity. Now, what about if I do it this way? If I, circle the, intermediate elements in this equation, and I got a completely different interpretation, because they are identical, right? So these orange, circles are just a guide to the eyes. This tells us what kind of combination that I'm interested in. If I'm interested in this identity, then this should be the way to look at. But if I look at this in the middle circle, what is this? This is nothing but a matrix element. This. Why? Because remember, this V carrying the hat, is just some kind of n by n matrix, right? And if this alpha primes living on the left, this should be what? A row matrix. And which is what? 1 by n. And if this alpha double prime staying on the right, and this should be a column matrix, which is what? n by 1, right? So then you multiplied 3 matrices with a 1 by n times n by n times n by 1. What you have at the end of the day is just a number, right? Because 1 by n by n by n by n by 1. So you get 1 by 1, which is a number. But what is a number? So it tells us that if you have an initial states labeled by alpha prime and the final states by alpha double prime, and this matrix element is telling you precisely the probability or the strength of such a scattering event, right? So this is a number associated with the probability amplitude of such a single particle scattering. And this is nothing but the matrix element, V alpha alpha prime. Okay? So this is the magic that you could re-express your single particle potential operator in terms of the matrix element of that operator, and then the Dirac Broglie cascade. So this is a cascade, and this is a Broglie, right? So, but what is this? This is nothing but n by n matrix. Remember your high school mathematics. Don't forget. So this is n by 1 as a cat, column matrix, and this is a number, which is just 1 by 1. So you simply just forget about this number. You could just put it everywhere you like. And this Dirac Broglie is what? 1 by n, right? Okay? So now you take the product. N by 1 times 1 by n, you get n by n matrix, which is exactly what we expect. Okay? Good. So now we finally arrive such a n by n matrix by rewriting the Schrödinger representation in terms of a Dirac notation. So in other words, this potential in terms of Dirac notation is nothing but n by n matrix with a matrix element V alpha alpha prime. So let me just rewrite this one more time. So we get V, which is sum over alpha alpha prime, alpha alpha prime, and alpha alpha prime. So now you enjoy this magic show, right? Because this is just a number. But this is a matrix. This is n by n matrix. So now we could finally define this creation and destruction operator. So let me just try to do that. So let me just use this kind of a n by n matrix as an operator, and I try to act this operator onto this any eigenstate alpha of the single electron in the box, and see what happens. So well, I apologize for this confusing notation. So this I could use this alpha prime, alpha double prime here, but so this alpha prime, alpha double prime, head-to-head represents precisely this matrix here. And since this is a matrix in quantum mechanics, this should be the operator, and this operator should operate onto any quantum states. Say this is the Dirac cascade alpha, and let's see what happens. Well, again, we could simply just encircle this 2 in the product, where we know that this is nothing but the inner product between a Dirac Broglie alpha double prime and Dirac cascade alpha. And by orthonormal condition, this is nothing but the Dirac delta function alpha alpha double prime, right? We have introduced that Dirac delta function as a normalization condition for inner product between this Dirac Broglie and cascades. Okay, so which means that when alpha is the same as alpha double prime, and the final answer is actually alpha prime, if they are not equal and you get 0, what does that tell us as an operator? So this as a quantum mechanical operator when it acts on this any arbitrary state alpha, it tells us that it destroyed the states alpha double prime, and it creates the states alpha prime, right? Because when this operator is acting on this alpha, and the final answer is only 0 or alpha prime, so that the original state alpha double prime is gone, is going away, and instead it creates this alpha prime. It destroys this alpha double prime and creates alpha prime. So it has this physical interpretation based on the Dirac notation. So it kills this alpha double prime and it creates this alpha prime. We're almost there. This is the definition of a destruction and creation operators. We're almost there. So in other words, if each of this alpha or alpha prime represents a single particle in certain eigenstate, and interpretation of this operator tells us that we destroyed a single particle carrying quantum number alpha double prime, but we create another quantum particle carrying the quantum number alpha prime. In other words, that's precisely what we mean here by single particle scattering. So when we have such a single particle scattering, we sort of we destroy an incoming state. Suppose that these two electrons are not the same before and after. Then we destroy the incoming particle and we create another new particle. So each morning when you wake up, you are not yourself anymore, because yourself living yesterday was dead. You say goodbye to you from yesterday, but a new guy is born today. And this is precisely what it means here. Of course, it's the same single electron, but we can effectively consider as destroying that incoming particle, but you create another particle. Okay, so this is the beginning of second quantization. So we will define properly next time how to quantum mechanically destroy a quantum state and create another new state. So in that sense, we can actually define a quantum mechanical operator to really kill a quantum particle or quantum state and create another one. Okay? So it sounds like a magic, right? So it all comes from quantum mechanics plus Dirac notation, but we could rewrite and re-express and manipulate those identities, and we could reinterpret this in terms of creating and destroying a quantum particle like this. So if you are not familiar with the Dirac notation, please review your quantum mechanics 1 and think about this notation. So you could check Flansburg's, our textbook, or Kittel's second book for this notation like this, or even David Pine's old book. So I guess that's enough for today, and I hope you enjoy this quantum mechanics in solid state, and I will see you next Monday.